So here is the main repo we'll be using for the training today. So if you go to the DeVito codes organization on GitHub, then the Energy HPC 2023 is the repo we'll be using. If you want a more interactive experience with a tutorial and you want to run some DeVito yourselves and play around with the different options during the workshop, then if you haven't got DeVito installed locally, maybe we can help you with that during one of the breaks. But also the easiest way of doing this is probably to make use of Google Colab. So if you just copy that link, if you head to the Colab page, click on the GitHub tab, and then type in the DeVito codes Energy HPC in the URL, and this should shortly hopefully find all the notebooks in the repository. And there it goes. Yeah, and then if you click on any of the notebooks, what you'll need to do then is just add some code cell and add the line pip install DeVito. Execute that, and then, everything should be ready to run then. But yeah, as I said, we'll get going at 9, but any questions about that in the meantime, or if anyone wants to go and grab a coffee before we get going, feel free to do so. So just to go over connecting via Colab once again. The first thing to do is go to this website on GitHub here. It's a public website, so you don't necessarily need to be logged in to GitHub or anything to be able to view it. And then down in the README file, there are some instructions for what to do with Colab. There's a link there. So you copy and paste this bit here. So this is the link to the repository where all the notebooks for today are. And if you click on the Google Colab link, that'll take you to this page. On there, click on the GitHub tab. Yeah, then on Colab, you click on the GitHub tab, and under enter a GitHub URL or search by organization or user, pop DeVito codes energy-HPC-2023. It'll take a minute, but then eventually it should find all the notebooks we're going to use in today's session. And then, the first one we'll be looking through is this 01 Introduction -DSL notebook. What you'll need to do in there is add a code cell and the line pip install DeVito. And run that cell then. But I'll leave this up. And if anyone's got any questions before we get going or needs help getting that set up, just give me a shout. Okay, good morning everyone. It's 9 o'clock, so let's make a start. So I'm Roger Nelson from Imperial College London, and together with Ed and Zoe, also from Imperial College London at the back in the DeVito t-shirts will be taking you through this workshop on From Zero to DeVito. So the workshop comes from a starting point. If you have some knowledge of SymPy and NumPy, then we'll take you from using the basics of this domain-specific language, which I'll say more about in a second, to build wave propagators, and finally, towards the end of the workshop, we'll get on to building a little FWI framework with DeVito. So DeVito is a domain-specific language for specifying or solving PD boundary value problems using the finite difference method. So it's a general purpose finite difference language for solving all sort of problems of this kind. We'll be focusing today on problems of interest in sort of seismic wave propagation, but sort of to emphasize the language can be used to solve all kinds of other problems. So Zoe gave a poster yesterday about how she used DeVito during her master's project to do modeling of the spread of COVID in cities and so on. And when we say sort of domain-specific language, what we're saying is that the syntax of the language is dedicated towards being able to express these sort of PDEs in terms of the sort of the finite difference method, which we'll see as we go through the various notebooks this morning. So the workshop is going to be split into 4 notebooks. We'll take a little break after each. So the first notebook will go through the basics of the DSL and just see how we express these PDE boundary value problems using the language. Next, so after expressing a problem, what we do is we're going to build an operator, and these operators is where all the magic of DeVito happens, really. So this takes your high-level SymPy style specification of this PD boundary value problem, and then DeVito takes that, puts it through a load of optimization loops, and creates some optimized C code for you. And so for the second notebook, we'll see some operators in the first notebook, but we'll go through we'll go through that in a little more detail, and some of the arguments and so forth we can pass to operators in the next notebook. And then after that, we'll move on to looking at how we can build wave propagators with DeVito of the style which may be of interest for sort of building FWI algorithms. And then finally, we'll go on to actually build a little toy FWI problem and see how DeVito fits into that. And so something to point out is that the first 2 notebooks of the morning, there we'll be focusing on what is the core DeVito DSL. The second 2 notebooks, where we build these propagators and build our little toy FWI framework, that'll be using abstractions which are built on top of DeVito, which we do specifically to demonstrate how one may wish to fit DeVito into these kind of frameworks. But I should emphasize that the second 2 notebooks are using these abstractions sort of built on the core DSL. They're not the core DSL themselves. So if you were thinking about using DeVito within one of these frameworks, you would probably want to build these kind of structures yourselves, to be able to handle your different types of, so how you deal with data, or if you do shot parallelization in different ways or so forth. But here we've just chosen one specific. Well, we'll just go through these sort of specific examples, but to emphasize that they're not actually part of the core DSL. And if you have any questions about that later on, of course, feel free to ask. Okay, so let's move on to sort of. So let's get going with learning about the DSL. Oh, and I suppose one thing before I get going with that, of course. So when we design these workshops, we try and optimize the material for sort of the mean participant who comes along to them. But everyone tends to come from quite different backgrounds in these things. So, of course, if you have any questions or so forth, if anything is a little bit unclear, yeah, please give me a shout and I'll be happy to sort of elaborate on anything appearing in the notebooks. So we'll start off for convenience. We'll sort of commit a little crime in Python, which we don't normally, which we wouldn't want to do in any sort of real piece of code, but we'll just import everything from Devito. And so in this notebook, we'll be talking about a few of the basic but sort of most important objects we use to construct these PDE sort of propagators. So we'll introduce the grid object, functions, time functions, equations, and then we'll sort of touch on the operator before we talk about it in more detail in the next notebook. So if we're gonna solve some partial differential equation using the finite difference method, the first thing we want to think about is our computational domain. So to do that, we're going to need to construct a grid. So the first object we'll see is the grid object, which exists in Devito. So if we have sort of the outline of our computational domain here, so here we have a grid. Its origin is at 0, 0. It has sort of an extent then in each of 2 dimensions. We're talking about a 2-dimensional grid here. And if we do want to define an object such as this in Devito, we can call the grid object, and the minimum amount of parameters we can pass to that is just to give it a shape. We'll also give it an extent here. So we're going to say we want to create a computational grid which has 5 nodes in the x direction and 6 nodes in the y direction. And then the physical extent of this grid is going to be 1 unit of length in each of those dimensions. And then if we, after creating our grid object, if we print it, you can see we have then this grid with an extent of 1 and 1, shape of 5 and 6, and it's automatically being assigned the dimensions x and y. So you can, if you like, define your own dimensions, but by default, Devito will just use the standard x, y, z dimensions for any 2 or 3-dimensional grid you define. After defining a grid, if you want to do some sort of calculus in finite difference land, we're going to need to be able to define some functions. So Devito has 2 core types of functions that we'll cover today. The first one are just functions which vary in space only, so there's no time dependence of these functions. If we want to define a function of that type, we have this function class, and this class, it behaves a bit like a SymPy function. So you can differentiate, you express derivatives of it in the same way you could sort of any SymPy defined function, but then it has sort of data management associated as well. It knows about all the function values at all the different grid points and so on, which we'll see shortly. And for any Devito function or any of the Devito objects we'll introduce today, if you want to get some more details, see some examples and so on, they've all got detailed doc strings associated with them. So if we pick any particular object, and we use the __doc __, then that will give you a detailed representation or a detailed description of what this object does, the core parameters, optional parameters, and some examples and so on. So just remember, any Devito object you want to get some more information about, you can just look at his doc string. Okay, so now let's create a function on our grid. So to create the function, we need to give it a name, and we need to tell it which grid this function exists on. This is the most the simplest manner in which we can create a function, pass it a name, give it a grid, and then if we print that, we'll get the mathematical representation of our function. And it's, as we can see, because we placed you on a grid with the dimensions x and y, it's then adopted those dimensions. If we want to look at the data associated with the function, that is the value of that function at each of the grid nodes, then we can look at f.data. If we print that out, you can see here that in the x dimension we have these 5 grid nodes, and in the y dimension the 6 grid nodes, owing to the shape with which we defined our computational grid. And as I mentioned, sort of the function object is going to automatically adopt the dimensions of the grid, and if we created a 3-dimensional grid, then the function would automatically adopt the z dimension as well, which I think we may see later. I don't remember. So that's functions which vary in space but not in time. If we want to define a time-dependent function, so a function which also has the time dimension in it, then we call the time function object. So it's very similar to how we define functions, but now we call time function. Again, we give it a name and tell it which grid it exists on. And then when we print out our time function, we can see it now has the added dimension of time as well as the 2 spatial dimensions, x and y. So since the default order of a time function is 1, if we print out the shape of our function g, it'll be allocated 2 buffers to represent our function at t and t plus dt. So if we print out g.shape, we can see it's got a length of 2 in the time dimension, and then the grid dimension or the grid shape in the x and y dimensions. We'll talk a bit more about how we can define functions with different time orders and so forth later, but by default it's going to, if we don't tell it anything, if we don't tell Devito anything else, it's going to create a time function which is able to store the data at the time t and the data at the time t plus dt. So next, let's look at how we can form finite, or how we can use Devito to form finite difference sort of propagators. To do this, let's have a quick recap of the finite difference method and see how that sort of links up with how we express these things in Devito. So if we go back and recall the definition of the Taylor series. So if we're expanding our Taylor series in the x dimension, so we have a function of x and t. There's just one spatial dimension here. This is, of course, generalizes to any amount of spatial dimensions. Then the Taylor series is given by this expression here. And if we rearrange the above expression so that we have this term, the df dx, is equal to something, then we get the following. So we get our function of f at x plus h minus the function at xt divided by h, and then this other stuff here. And provided h is small, we can say that df dx is approximately this expression here, which will then have an associated error given by all these terms we've left out. So this is the well-known forward difference approximation, or the right derivative, as some people like to call it, and is how sort of derivatives are approximated in space order 1 in finite difference schemes. That's what we mean by the space order, that we're throwing away terms of order, we're throwing away terms of order space order plus 1. So we're throwing away h squared terms here. So we say that our scheme is of space order 1. We can also write the backward difference approximation by taking the Taylor expansion around x minus h. When we do that, we'll get this expression for the Taylor series. If we rearrange again and throw away terms of order h squared or greater, then we'll be left with this expression here. Now, if we want to look at how we can approximate or how we can represent these two things in DeVito, if we want to express the right derivative or the forward difference, we can say f dot dxr. And if we want to approximate the backward difference, we can say f dot dxl. When we print these things out, you'll just see that it's telling us we've just specified the derivative of our function f for both of them. You can see there's no difference between what DeVito is printing out here. But if we want to actually see the underlying finite difference scheme associated with that, associated with this symbol, we can say f dot dxr dot evaluate. If we do that, we can see what the finite difference is associated with that particular object. And you can see then, yeah, for the right derivative, we have this expression here, and for the left derivative, we have this expression here, exactly the same as the ones we wrote down above from rearranging our Taylor expansions. And so just to point out, there is the centered derivative then. If we just print f dot dx evaluate, but for first order, of course, there is no centered difference approximation of first order, and hence they'll just print out the forward difference method in that particular case. And here is and then here's a summary of just what I mentioned above. So that's going over the using Taylor series to form our finite differences for spatial derivatives. We can of course do the same thing with time derivatives, and so if we have some function u of x, y, and t, we want to express the forward derivative of that with respect to time, then we have the same approximations, so the forward difference in time. So where our u is evaluated at t plus delta t minus u over delta t is the first order approximation for the time derivative, where delta t then is some small increment in time. Oh, thank you. So now let's take a simple PDE and look at how we use what we've learned above to express a time-stepping scheme. So for this, we'll use the linear convection equation. So the PDE we want to solve reads du dt plus some constant c times derivatives in both of the spatial dimensions. Now, if we discretize the temporal term, to start, then we have this u at t plus delta t minus u over delta t. So we just use the forward difference in time, the first order forward difference in time approximation, then plus spatial terms. So we can rearrange this then in terms, so we have that t plus delta t on the left-hand side and all the terms at time level t on the right-hand side. So we'll form an explicit scheme, explicit time-stepping scheme here. And then we have that u at our next time level, t plus delta t, is equal to u minus delta t times the constant c m times the spatial derivatives. Now to complete a finite difference schemes, we then need to discretize the spatial terms, and here to do that we'll use the backward difference approximation of the first derivative for each of the spatial terms. And if we substitute those expressions, which I wrote down in above, we will get the following scheme. And then you can see, providing we know what our function u is at the time level t, then this gives us a way of computing our u at the time level t plus dt. And so if we're given some initial condition at time equals 0, say, we can then compute the evolution of our field u forward in time. So let's now take an example and look at how we build a scheme to solve this particular problem in DeVito. So for this, we'll just define some sort of model, well, define some of the parameters we need to define for the scheme. So we'll say we want to run our model for 100 time steps. We're going to define a dt, and we're going to choose a value for our constant c. We'll just set it to be equal to 1. And next, we create a grid on which to define our function u. So we're going to create a grid which has a shape of 81 nodes in the x dimension and y dimension, and the spatial extent of the grid will be 2 in each of the x and y dimensions. Then we can define our function u on this grid. So we give it a name, pass it the grid, and the next thing we want to do is set our initial conditions. We want to set what our function u looks like at the time level 0. We have a function. I am using this as a helper function here. We just call that, and this is going to give us this initial field. Right? We've just chosen this initial field, and then we're going to put this into our linear convection equation and look at how it evolves in time. So next, we need to define our PDE in DeVito. To do this, we're going to need to introduce ourselves to a new DeVito object, which is the equation object. This is just a way in which DeVito understands the sort of expressions of PDEs. It's very similar to the equation object in SymPy, if you've used that before. But what we see is when we express this equation, we write it down in a very similar way to how the mathematics above looked. So we're saying that our equation is u dot dt, so the derivative of u with respect to t, plus constant times the left derivative of u in the x direction, and plus c times the left derivative of y in the y direction, and then the right-hand side is equal to 0. So after we've created our equation object, we can look at, we can print it out and see what that looks like. And here we go. We've got the mathematical expression which DeVito is going to take, and you can see that just is the same as the PD we wrote down above, but of course here with c set to 1, and so that's been factored out. So next we want to create our time stepping scheme. So we're going to define our stencil, which is going to be the right-hand side of our time stepping scheme, and we're going to call solve on the equation, and we're going to say we want to find out, we want to put u dot, and we're going to solve our equation above for the variable u dot forward. So so basically what this line is doing, it's finding out what the expression for u dot forward is for us according to the definition of our equation here. And then when we've done that, we can create our update equation. This is the final time stepping equation which we're going to pass to DeVito. And we say that equation u dot forward, comma, then the right-hand side, which we computed above using the solve, and that's our stencil. And then if we print out our update equation, you can see what it's doing here, and u at t plus dt is equal to this stuff here. And if you can compare the mathematics, that's exactly the same as the update scheme we wrote down when we worked everything out by hand. And if we want to see the finite difference representations of the spatial derivatives as well, We can just use the evaluate method again, and then that gives us the full update scheme. Again, if we go through and multiply out or cancel out some of these DTs here, you can see that's exactly the same as the upstate scheme we wrote down when we worked things out by hand above. Next, before we run our simulation, we just want to set a few boundary conditions. So we want to, our initial distribution on the boundaries, it has a value of 1, and we want to keep that, so we want to set the value of our field u to be 1 on the boundaries throughout the simulation. So let's look at how we can do that. For that, we need to specify a few more equations. We'll specify one equation for each of the boundaries. So we're gonna grab the dimensions of our grid. So we'll say x dash y, or x comma y is equal to grid dot dimensions. We're also going to need the step-in dimension. I'll explain a bit more about this in a second. And then we're going to define boundary conditions for our left boundary, right boundary, top and bottom boundary. And what we're saying for them is this expression is saying that we want u, our field u, at the next time step, which is what this t plus 1 indicates. Again, I'll go through exactly what this step-in dimension is again shortly. But it's saying that the next time step on the left boundary, so the x equals 0 node across the entire of the y dimension, we want the value to be 1. So you can see at the end, well, at the end of the sort of the time loop, before we go on to the next iteration, it's going to apply this equation and set that value of that particular boundary to be equal to 1 as we desire. And then we do the similar thing for the right boundary, the top boundary, and the bottom boundary. Okay, so let's just talk a bit more about exactly what this step-in dimension is. So recall that owing to the manner in which we defined our time function, you will have a size of 2 in the time dimension. So to minimize memory footprint, unless told otherwise, so DeVito will use modulo time step-in. So it's going to store the minimum number of time steps required for any particular numerical scheme. So the attribute time dimension of a grid tracks the overall number of iterations, hence the simulation time. So if we wanted the total number of iterations being carried out, we could grab grid.time dimension, and the actual simulation time would be grid.time dimension times dt. Whilst this grid.step-in dim keeps track of the modulo time step, right? So if we're evolving hundreds of time steps forward, but we've only got a length of 2 in the time dimension, you can see we're going to keep having to overwrite the time buffer as we move through the simulation. So what this grid.step-in dim is, in this particular case, it's going to be time dimension mod 2. Or basically, it's in a general case, it's going to be time dimension, or it's going to be the time dimension mod length of the buffer in the time dimension of our function. So with a size of 2, so here's a table to summarize exactly what's going on. So at initially, sort of at time 0, the simulation time is 0, and our function u, that initial data is going to be stored in index 0 in the time dimension of our function u. Then at time 1, or at time step 1, the simulation time is going to be tt, and then the data or the data of our field u at this particular point in time is going to be stored in the index 1. After 2 time steps then, when we're at simulation time 2dt, it's going to go back and our field u is then going to be stored in the index 0, and so on. So we're going to keep doing this sort of modulo time stepping through this particular scheme. In the next notebook, we'll see some ways where we can store the entire field if we so wish, but by default, this is the behavior. So finally, we need to create and execute a DeVito operator, and this is where really all the magic of DeVito happens. DeVito is going to take the symbolic specification of the boundary value problem, and through a number of compiler passes, produce C code optimized for the target platform. And so to create our operator, we call the operator object, and we pass to it a list of the equations which specify the boundary or the PD boundary value problem of interest. And then this prepares our operator, and then to run it, we give it an end time for the simulation or an end number of iterations, and we tell it what we want the DT of our simulation to be. And then this calls and executes the operator, and then if we print what our field U looks like at the end of the simulation, you can see sort of, as expected, it's been vectored through the domain a little bit. If we want to see the C code, which DeVito is sort of running under the hood, we can do that by printing out the op.c code. And then this is going to show us exactly what DeVito ran to produce those results. And just a quick, well, just to highlight some of the points here. I won't go through in too much detail, but here, this is the expression of our finite difference scheme. And then down the bottom, we have the specification of our boundary conditions, where sort of these values of 1 are being set at the required nodes. And just to quickly point out some of the optimizations we can see DeVito has made during the production of this code. You can see for common floating point operations, then it's recognized that these operations are done a lot, and hence it's created these variables. So it's moved, created a little bit of additional memory pressure in order to reduce the required sort of flop count of this loop by specifying these particular variables. And there's a whole host of different optimizations DeVito does. There's a whole host of different. When we create our operator, we can pass different. So when we create the operator here, we can pass different sort of optimization levels to it, and depending on what you want, it can optimize more aggressively. This is just using the basic one, so it'll do some basic optimizations. But one thing about the basic one, it does leave the code readable, so we can understand what this C code. We can look through this and sort of recognize what's going on. If we use some of the more aggressive optimizations, then you can often end up with C code which is sort of fairly comprehensible to the sort of the human eye. Okay, so that's sort of running a sort of a basic PD solve with DeVito. Let's talk about now some of the other sort of options available in the DSL. So there's various shorthands available to make expressing sort of these finite difference schemes more convenient. So for our time function v, if we want to point forward in time, which we're frequently going to need when we're setting up our time stepping schemes, there's the shorthand g dot forward. If we want to point backward in time, we have the shorthand g dot backward. And for any of these shorthands, these are just another sort of symbol, if you like, and we can do calculus with these expressions as well. So we can say g dot forward, g dot forward dot dt, which is going to then give us the derivative of g at t plus dt, and so on. And same, we can take spatial derivatives of g dot forward if we wish as well. So when we get on later to build in wave propagators to keep things sort of simple and sort of and to fit everything within the time constraints of this workshop, we'll build things using the second order wave equation. And of course, to do that, we're going to need to be able to define second order derivatives and so forth. Let's see how we can define higher order derivatives and higher order sort of schemes in DeVito. So if we went back to the Taylor our expression of the Taylor series earlier, remember we had this we had the backwards or the forward difference approximation and the backward difference approximation. Well, if we add those two things together and rearrange, we can end up with an expression for the second derivative of our function with respect to x squared as follows. This is the expression we'll get there. And then for this, we're throwing away all terms of order h cubed and higher, and so this is a second order scheme. And if we want to implement this derivative in DeVito for our function f, we can say f dot dx2. However, I didn't run any of this, so I'll need to just quickly run through this. But if we try and run this with the current f we've defined, we will see the following. Now we'll see that we're getting an attribute error, sort of f object has no attribute dx2. So let's review the function documentation again. And in this documentation, if I can find it, here we go. Space order. So there's an optional parameter you can pass to functions when you create them. And here it's saying that it defaults to 1. And hence, as we saw above, this is a space order 2 method. But because we created our function in the default way, it is only space order 1 and hence doesn't understand these space order 2 methods. And and hence why we're seeing this error when we try and take a space order 2 derivative with respect to this function f. But now, if we redefine our function f, so again we give it the name, pass it the grid, but now we're going to pass it the explicitly tell it that it's a space order 2 function, and then when we take the second derivative then, and if we evaluate that just to see the scheme we're getting, you can see then it understands what to do with this definition in place, and it's just pointing out exactly the finite difference scheme or the finite difference approximation for second order derivatives that we wrote down above. If we want to go to, we can extend space order to be arbitrary. As you know, we can ramp it up as much as we like, I suppose within reason. I don't know what the highest scheme anyone's ever tried, but I'm sure some people have put in space order 100 schemes just to see the stencils which get produced. Not that you're going to use that in practice, but If we want to, for example, get a fourth order accurate approximation for the first derivative, this is the finite difference scheme for that. If we work it out using the Taylor series based approximation, and we can do that as follows. So if we just define now our function f with a space order of 4, and then we say f dot dx dot evaluate, we'll get the scheme here. So by default, Devito will produce schemes with the order space order used when defining a function, but we can override this if we like by explicitly passing the space order of the desired scheme when creating a symbolic expression for the derivative. So for example, our function f is defined here with a space order of 4, but let's say we want to produce a scheme which is order 2, then we can say f dot dx, fd order equals 2, and this reverts back to this is just then the forward difference method. A quick note there. As we said, the first order difference method is only actually first order, so it's not second order. So I suppose you could ask the question, well, why when we've said fd order equals 2, we're only getting this approximation? And this was just sort of a design choice, because the second order approximation is the centered difference method, but that's sort of dangerous to use in a lot of forward propagators. It ends up with lots of instabilities. So by default, if you just say fdx and ask it to produce a second order scheme, it will revert to the first order approximation for the first order forward difference method. If you do really want a second order centered difference scheme, there's the f dot dxc. F dot dxc is available to you, so to get the second to get centered difference. And generally for higher order derivatives, the default x dot dx is equivalent to f dot dxc and so on. It will by default give you a centered difference method. It's only for the second order case where it behaves differently. So as we said above, but just a reminder, so there's a note that the FD order cannot exceed the space order with a function which was defined. So if we've defined this to be a space order 4 function, and we try and override it with say FD order equals 6, it's just going to throw an error again and tell you your function wasn't defined, or that attribute doesn't exist. The time derivatives follow a similar principle. So we simply sort of pass the desired time order to a function instead. So if we want to define our function g, I have a time order of 2 and a space order of 4. And then we can play around with the syntax to give us all kinds of different derivatives and so on. So taking the second derivative in time, the first derivative in space, in the y dimension, then you can see that we're getting, for the spatial derivative, we're getting the second order accurate scheme we defined with the time order 2. And in the spatial dimensions, we're getting the fourth order accurate approximation. So to implement the diffusion or wave equations, we're going to need the Laplacian. We have a convenient shorthand available for doing this. And now, before we have a look at that, let's just define a 3-dimensional grid. So we're going to create this grid 3D. We're going to pass it shape, so it's going to have 5 nodes in the x dimension, 6 nodes in the y dimension, and 7 nodes in the z dimension. And it'll have a spatial extent of 1 in each of those dimensions. Then if we want to define a function from this grid, we just pass it the grid 3D. And we're going to tell it that it's got a space order of 2. Of course, if the Laplacian is second order derivatives, and so it's going to need a space order of a minimum of 2 in order to be able to define the Laplacian operator. And then I create and so we could, if we like, just so there's the shorthand available, u dot Laplace, or if we want sort of a 12th order Laplacian, for example, we can just say space order 12 and sort of run u dot Laplace here. Let me just run these so you can see the actual stencil which gets created. Where's the grid? Let's run that. And then, and so in this this quick line of code, then we've created this sort of 12th order sort of Laplacian operator. And we should note that we could, if we like, do exactly the same thing by expressing the operator explicitly. So if we do u dot dx2 plus u dot dy2 plus u dot dz2, we will get exactly the same thing. But of course, one of the nice things about having the Laplace operator is that this is sort of agnostic to the number of dimensions. It's just going to work out how many dimensions are in your sort of definition of your function u. So finally, before we finish up this notebook, just show that we can take derivatives and so on of composite expressions. So if we've got two functions, two-time functions u and v, we can take v dot dt2 plus u dot Laplace if we like, but then the resulting expression we get from this, we can further differentiate that again if we like. And here we go. This is one of the stencil which gets produced by doing that. And just to say that we can produce or use this syntax to keep sort of repetitively doing any sort of finite differences we want and create these sort of arbitrarily complex expressions. Okay, so I guess, so that's the first notebook. So let's take a 7-minute break. And then when we come back, we'll move on to the notebook on operators. And of course, any questions you have in the meantime, please give us a shout. Okay, let's make a start back. So in the next notebook, we'll talk a bit more about operator, and in particular, the apply method and the operator.arguments. So we saw this method in action in the first notebook, but we didn't really draw attention to it. But we'll sort of show what happens or the different ways in which we can actually sort of apply or execute these operators in this notebook. And then we'll look at what arguments can be passed to an operator. So what are the default arguments and how we can potentially override them if we wish. So to start, we'll import a few of the objects from Devito we're going to need in this notebook. So we'll grab the grid, the time function, the equation, and the operator objects. We'll start off by creating a grid. We'll pass to that a shape of 4 and 4. You notice sort of when we created a grid in the first notebook, we also passed it extent, but we're not doing that here. And by default, again, if you check the docstring, you'll see that Devito will assume an extent of 1 in each of the dimensions if it's not explicitly specified. Now we'll create a time function u on this grid, but now we're going to pass a new parameter to this time function when we create it, and that's going to be save equals 3, which we'll learn about a bit more about exactly what this does and sort of what it means shortly. So now we can create an operator. Our operator is a very simple one. We're just going to say that u at time t plus dt is equal to u at time t plus 1. Okay, so we're just adding 1 at each iteration. So to run an operator, we need to apply it. So we can say, and we're going to say summary is equal to op dot apply. So when in the first notebook, when we called operator, we didn't use this apply argument. We just called op, then open our curved brackets and something. And that's how Devito, so if we don't explicitly call the apply method, this is how what Devito does with operators. It runs the apply method. So what I'm saying is that this, executing that. So if I said summary equals op, open and close my brackets, that is really just a shorthand for op dot apply. When we run that, this is the method it's really calling. And it'll run our operator. So now if we look at our dimensions, so we have time x and y as our dimensions for our function u. And if we look at a shape, you can see the shape is 3, 4, and 4. So when we defined our function, right, we didn't override the default time order of the function. So the default time also, and then remember the default time order is 1. This is a time order 1 function. But we've added this save equals 3 argument, and because of that, the function u is being created with a length of 3 in the time dimension. So if we pass this save parameter, the length of the time dimension will just be set to whatever that save parameter is. And this is going to add some constraints to what we, or how we can use this function in operator, which we'll see shortly. But then this is if we, for example, we're running a forward wave propagation and we want to save the entire wave field. So we need to, if we're going to compute the gradient, if we're going to create the gradient of an objective function within an FWI algorithm, for example, we need to know the entire forward wave field, and this is the parameter which then allows us to save the entire thing, just specifying an appropriate save. But when we've then run our operator, you can see it's just applied it and filled the time. We'll just run the operator as much as it can to fill this, or to fill the data in each of the time dimensions. So U has a size of 3 along the time dimension since it was built with save equals 3. Therefore, OP could only execute 2 time steps, so namely time equals 0 and time equals 1. So given U EQ U dot forward is equal to U plus 1. So executing time equals 2. So if we try to sort of execute an additional time step, that would have resulted in an out of bounds memory access error. So Devito figures this out automatically and sets the appropriate minimum and maximum number of iterations. When you use the save parameter, unless Devito will automatically figure out how long to run the simulation for based on the size of your, based on the length of your time dimension. And so note that at all 16 points, then in each time slice of the 4x4 grid, this U plus 1 is being computed. So if we want to see the default arguments, or we want to see the arguments which an operator is using to perform these computations, we can print op.arguments. So there we see sort of this range of variables DeVito is using when it runs this operator. Let's look at what each of these mean. So time underscore little m. So this is the smallest or the first iteration DeVito is going to execute. So this is going to start at time 0 or start at time step 0. Time size is the length of the time dimension, and time underscore big M is the final iteration which is going to be executed. So in this case we can see, and this has been, these have been computed automatically sort of based on the specification of the operator. So if we can see what we mean exactly by that. So the first time step is time step 0, which is going to fill the sort of memory buffer at time equals 1. Then we run time equals 1, which is going to fill the memory buffer at time equals 2. And so then we've used up our three buffers in the time dimension by executing those 2 iterations. And so that's why DeVito has picked these, because we defined time size to be equal to 3. So xm, x underscore little m, x underscore big M, and x size, they mean similar things, but they are for the x dimension data. So x underscore little m, that's the smallest index in the x dimension upon which DeVito is going to execute the operator. And x underscore big M, then the largest. Of course, Python indexing starts from 0. So our grid is 4 by 4, and hence the indices go from 0 to 3. And similarly for ym, and then hx and hy are the spatial extent, or the spacing, the grid spacing in the x and y dimension, and ox and oy is the origin. So we didn't specify a particular origin, and by default, again, DeVito is going to set the origin to be at 0, 0. So u stores a pointer to the allocated data. So timers stores a pointer to a data structure used for sort of C-level performance profiling. So this is the final thing here. And so one may want to replace some of these default arguments. For example, we could increase the minimum iteration point along the spatial dimensions, x and y, and yet execute only the very first time step. So let's play around with some of these arguments by changing them. So let's reset our data first. So we're going to reset all the data in our function u to be equal to 0. And then we're going to call our operator again. But now we're going to tell it x underscore little m is equal to 0. But y underscore little m is equal to 2. And we're going to tell it that the maximum, the largest iteration we want it to compute is time underscore big M is equal to 1. And then if we look at our data, so this x underscore little m, of course, that's the default argument, and so it's going to run it on all the nodes in the x dimension. But our y underscore m is 2, and hence now it's only iterated on the final 2 nodes in the y dimension, because we've changed this default argument to tell it to do so. So given a generic dimension d, the naming convention is as follows. So d underscore little m is the minimum iteration point, and d underscore big M is the maximum iteration point. Of course, follows over to the time dimension as well. So hence op.apply, and if we've got dm4 and d underscore big M7 for some generic dimensions, that's going to run op in the compact interval 4 to 7 along the dimension d. And for historical reasons, D equals something, alias is DM, D underscore big M to be something. So for historical reasons, you could use this shorthand if you wanted. But really, that's old DeVito for sort of people using old codes. The new syntax is to explicitly use this underscore big M and so on. So in many DeVito examples, it happens, or you may see something like time equals 10, and this is just an equivalent to op.apply time underscore big M is equal to 10. So this then is the old syntax. The time then is just equivalent to time underscore big M, i.e. the largest or the final time step which is going to be executed. So if we try to specify an invalid iteration extreme, so DeVito will raise an exception. So if we want to apply and tell our operator to run for up to time underscore little m is equal to 2. So in that case, we're trying to run we're trying to run 3 time steps, the 0th, first, and the second. So because our scheme is telling it to fill up u at t plus 1, that would require 4 buffers in the memory dimension to execute this scheme. But now we only have specified 3, and so this is going to tell us that out of bounds detected due to time underscore big M equals to 2. And the same operator can be applied to a different time function. So after we've constructed our operator, and that underlying C code has been produced, there are we can overwrite sort of anything we pass into it, really. So we can pass in although we constructed the operator maybe using a particular function, we can always pass in a different function to the operator then, and it'll just reuse that code. So if we create a new time function u2, and we say time function, define that as a time function on the grid with save equals 5, and then we call our operator, but we tell it to overwrite the default u argument with u2 to take our new time function defined, and then run that. It'll do that happily. And now it's done exactly the same thing, but because this is has a save 5, we've got a length of 5 in the time dimension, and it's gone and filled up all of those buffers. This run from time underscore little m equals 0 through till time underscore little m equals to 3. As time underscore big M equals to 3. So note this was the third call to op.apply, but the code generation and JIT compilation only occurred upon the very first call. Okay, so when DeVito needs to construct an operator and compile it, it'll do that, but it's not going to do that again unless you explicitly tell it. It's going to keep reusing this sort of little compiled library. There is one relevant case in which the maximum iteration point along the time dimension must be specified. So whenever save is unset, as in such case, an operator wouldn't know for how many iterations to run. So back in the first notebook, when we run our operator, because we didn't create our functions with save, and hence it was just using this, the minimum amount of time buffers needed to represent that time step in scheme. If we specify our functions in that way, i.e. without passing them the save parameter, then we need to explicitly tell the operator how long to run for. So again, so if we create now our time function v, and this is going to be again, so it's v4, we're just going to add 1. Now, if we try and run our operator, if we create an operator with this function, we try and run it without passing any arguments, it's going to tell us no value found for the parameter time underscore big M. So I'll assume time underscore little m is equal to 0. But in this case, we need to pass it explicitly what a time underscore big M is. Note if we look at the shape, because we specified this function with a time order of 2, now we have a shape of 3 in the time dimension. That is when we write out finite difference schemes of time order 2, they are schemes which rely on the time step -1, the current time step, in order to compute the time step at t plus dt. Now, if we set v dot data equals to 0, so let's just 0 our function, and then we will we'll call op dot apply, passing at time m equals 1. Now let's see what happens. So we have then, this is just filling up the 0, the 1, and the 2. So it's running for that 0th iteration, or it's running the 0th time step and the first time step, which then the first time step, of course, computes the data at t equals to 2. Now, above we were using the we were setting, when we were running our operators, we were saying summary equals to op.apply. Now this summary object, let's just print out what it gives us. So if we print this out, so that it contains various performance statistics. Currently, they are going to be sort of mainly empty. So by default, in order to save on compute or save on sort of computations, most of the performance indicators are switched off. It's just telling us how long it took to run the operator. If we do want to get these outputs, we can change the DeVito profiling environment variable. So if we do from DeVito import configuration, so let's set our profiling to be the advanced mode. And then if we create some operator and we run that operator, then you can see now we're getting additional statistics. So it's telling us the time taken to run the operator, so the gigaflops during that operation, the gigapoints, and so on. And there are various operations in terms of profiling you can play around with to check the sort of the performance of the operators being run on any particular piece of hardware. So a performance summary will contain as many entries as sections in the generated code. So currently there's no way to automatically tie a compiler-generated section to the user-provided equations. So in general, there can be more than one equation in a section. The only option is to look at the generated code and search for the bodies of code so wrapped within the C comments, such as if we got some begin section, then a piece of code, and end section, and then let's just take a look at what this gives us. I'll probably need to run a few cells to be able to show that. Let me just run through the notebook quickly. And then here we can see sort of these begin sections and end sections which get produced in the code. So in the performance summary associated to section 0 is a perf entry whose entries represent sort of time. So this is the time in seconds to execute that section. the gigaflops. This is performance of that section in gigaflops per second. Gigapoints, performance of the section in gigapoints per section. OI is the operational intensity. OPS, floating point operations at the innermost loop iteration, and iter shape, and this is then the shape of the iteration space. If you're sort of interested in any of those performance statistics for any reason. Okay, and that's it for the second notebook of the section. So now let's take, I guess, let's take an 11-minute break now then, and there's if anyone's interested, so during the break there's a little sort of exercise you can try, where we compare the result of a DeVito simulation to an exact solution of the second order wave equation. And sort of when we, and of course any questions about that during the break, I'll be happy to sort of answer and help. Ask Ed and Zoe as well if you have any queries. And sort of when we start back, I'll quickly go over a solution to this particular problem, but then before we move on to actually then producing a wave propagator for the acoustic wave equation using DeVito. Okay, let's make a start back. So just before the break, we posed this exercise. I didn't necessarily, most people who are new to DeVito, I didn't necessarily expect anyone to be able to solve this problem during the break, but it was just there to sort of allow you to start playing around and see, figuring out how to express things. Now I'll just go over a quick solution to this particular problem. So we're considering the 1D wave equation in a finite domain of length 10, and we have the initial boundary conditions that we have Dirichlet boundary conditions on each of the extents in the x, and on the left boundary and the right boundary, the velocity field of the wave is initially 0, and the wave is 1 between 4 and 6 in the x dimension and 0 otherwise. So we have this particular initial state. Of course, we can solve this particular problem exactly, and the solution we get is as follows, where our an are equal to these values here. And you can see then that the period of this wave, of course, is going to return to its initial step or initial location. If we pick c to be equals to 1, then the period would be 20 time units in that case. So potential, or one way we could solve this in DeVito would be as follows. So we define the length of our domain. And this is just going to be for plotting purposes. We're going to define the number of terms we're going to use in the Fourier, the exact Fourier expansion, just for comparison. And then L is the number of points into which we're going to discretize our spatial dimension. And then I'm just setting C to be equal to 1. So we'll create a linear space, so a set of evenly spaced 1001 points then in the x dimension, and these functions here are just for expressing the exact solution. And then this is a plot of then the exact solution at time t equals to 0. So now let's look at how we do set up our DeVito implementation of this problem. So we'll set our time order to be 2 and our space order to be 2. Here the minimum the minimum order of discretizations we can use, since this equation is second order in both space and time. We'll import some required functions. we'll create our grid, and we'll pass it the shape of 1001. So this is just a one-dimensional grid now. So we just pass it sort of a tuple with a single entry, and we pass it our spatial extent of L, which is equal to 10 in this case. We're going to use the modulo time step, and we're not going to save the entire scheme, and so we're going to need to grab the step-in dimension in order to sort of set our Dirichlet boundary conditions a little later. So then we can create our time function, our U, our wave field, give it the grid, and give it the time order and space order of 2, which we define above, and then we're just working out dx here, and then the critical time step in order for the simulation to be stable. We need to satisfy the CFL condition, which tells us that dt needs to be less than 0.42 times dx over c. So that works out to be 0.0042 in this case, but we'll set our dt a touch under that. And then also this is so that after a nice rounded number of iterations, the wave should return to this initial position. So remember, with c equals 1, the period of this wave is 20. So after 20 units of time, the wave should return to its initial position. And you can see that equates to well, I'll equate to 5,000 time steps with this dt. Then we write out our PDE. So we've got 1 over c squared u dot dt 2 minus u dot dx2. And then we create our equation. And we want u dot forward to be equal to the solution of our PDE for u dot forward. So this is just going to move u at t plus dt to the left-hand side, all the other stuff to the right-hand side, which gives us our time stepping scheme. And we'll define our boundary conditions, and this is staying at the next time step. We want the value at 0 to be at the 0th node to be 0. That's our Dirichlet boundary condition. And then the value at the final node, the value at the last node in the x direction to be equal to 0 also. So because this is a time order 2 simulation, so to compute the next time step, so to compute our field u at t plus dt, we need our field u at the time t, but also the field u at the time t minus dt. And hence it needs Devito in order to compute things correctly is going to need 2 initial conditions here. And it'll start computing, or it'll start the propagation problem from time is equal to dt. So it sort of knows it needs 2 initial conditions, and it starts from then the appropriate time. But we need to set our u dot data. We need to set the 0th index in the time dimension and the first index in the time dimension. And then the first computation Devito will do, because this is a time order 2 simulation, is to compute our u at time equals to 2 dt, or it's going to fill out u dot data 2. And to set those initial conditions, we're going to just use the exact solution. So this is set in u dot data at time equals to 0 to be equal to u naught, which is just the exact solution computed at that time, and u1 is the exact solution computed at time equals to dt. And then we'll create our operator, and we'll say our operator is equal to our equation and the boundary conditions. Just to point out, I think, initially sometimes this plus BC confuses people, but this is just pure Python syntax. So this we're just passing it a list of equations, and of course in Python you can add lists together through through using this plus operator. This is not a this is nothing to do with a mathematical plus operation. It's just simply saying we're going to create this longer list by adding two lists together. We could write this long list out explicitly as we did in some of the previous notebooks, if we liked. And then we run our simulation. So we'll start at time underscore little m equals to 1. Although, again, to point out that if we didn't pass that explicitly, DeVito would work out that that's what it should be doing. And then we want to run up till, the final time step we want to have data for is the 5,000th, and so we'll run up to the one before that, which will then compute data at time at the 5,000th time step. And we'll pass TT, and then we'll run this thing. And this is then the result we get back. So we can see there's, the wave is propagated across the domain and returned to its original position, but there's quite a lot of noise. There's been lots of numerical dispersion because of the square wave. But of course, we can play around with different parameters and so on in order to improve this result. So just a very quick demonstration that if we set the space order to be 12, for example, and let's just rerun everything with this increased space order. And you can see things have already started to improve a little bit, but then there were lots of other tweaks we could make to get a much better result. But that's just a quick demonstration of how we can implement these schemes. So now, we'll move on to, we'll solve the wave equation again, but now we'll set up this, we'll set things up so we're producing a wave propagator of the kind we might be interested in using within an FWI, the framework of an FWI algorithm. We're going to need a few new objects to be able to do this. We'll have to talk about sources and receivers. And so, of course, when we're if we're considering a forward wave propagation problem for some kind of imaging scenario, we start off where we produce a pulse of energy, which then produces the seismic waves. So this we do that in DeVito by using source objects. And then we need to then be recording this data at certain points within our grid. This is akin to our hydrophones or wherever we've got set up in a field experiment. And for this, we're going to be creating these receiver objects. So for this, though, in order to sort of not spend our time specifying various things we'll need by hand, we're going to introduce the model class. As I mentioned earlier, this model class is just a convenient abstraction based on DeVito to allow us to sort of quickly set these problems up. This, again, to emphasize, this is not core DeVito. If you were building your own framework, you'd probably want to build all these things from scratch. We're going to sort of introduce sources and receivers, and then we'll build our acoustic propagator. So this is the kind of scenario we'll be considering for solving our forward problem. We'll be have some domain with some subsurface with different velocities of seismic waves within that subsurface, and then we've got a source, some source of shock waves, which is going to fire, create the propagation of our seismic waves. We'll get reflections and so on, and there'll also be the direct signal to the receivers, and then we'll have our sort of receivers, which will mimic our hydrophone setup in our domain to then to detect or to measure the wave field through time at those specific points. Again, the wave equation we're going to use to do this, we'll keep things simple. So we'll just use the second order acoustic wave equation. If you sort of look through all the DeVito tutorials, you'll see there's a range of different wave equations. I've been sort of, well, there's tutorials introducing you to how to set up a range of different wave equations. And of course, you know, you're not limited to just using the ones which are in the tutorials. You can use the DSL to set up any wave equation you wish. So-called M is going to be equal to 1 over c squared. And we'll have that our initially, before our source turns on, sort of firing the seismic waves into the system, we'll have that everything is static. So we've got zero wave field and hence zero velocity initially in our domain. On our domain boundaries, we're going to apply Dirichlet boundary conditions. So we're going to set that the wave field is zero right across our boundary. But of course, in a seismic wave propagation problem, in a real scenario, of course, we're dealing with an essentially infinite domain. We fire off our waves; they are just going to propagate out. But as soon as we move to a finite domain, we need to start to think about reflections. We don't want reflections to pollute our results. Of course, there's a balance there between the computational cost of dealing with reflections, you know, versus increasing the overall sort of computational intensity of the simulations. For this particular setup, we're going to use a simple absorbing boundary layer. We do have tutorials available where much more complex PML layers and all these different types of things are set up. But for here, we'll just use a simple create the model. We pass it, we tell it what we want the velocity profile to be. So we define this V here, which was our two-layer velocity model. So we're going to set the VP, velocity of pressure waves, to be equal to V. In our model, we give it an origin, a shape, a spacing, which we all defined above. We tell it what the space order we want of functions in the model. And this is the main thing we're using the model for, is to specify the width of the boundary layer. So this MBL is a boundary layer width, and we're saying that we want the model to be 10, we want the boundary layers to be 10 grid points in each of the dimensions. And so we created here the shape of 101, and that defines the main computational domain. But because we've specified MBL to be equal to 10, that's going to extend the grid which gets created, and is going to be extension of that of 10 nodes in each direction where this boundary layer is set up. And so the computational grid used will actually be 121 by 121 nodes. And of course, we can change this thing as we like. Larger numbers of boundary nodes are going to result in less reflections, but of course then higher computational costs. So now we need to set up our acquisition geometry. That is the position of our sources and receivers for this particular problem. Here we're going to use a Ricker wavelet for the sources, and the signature of a Ricker wavelet is given by this equation here, and then that's going to be applied at sort of 1 point in space. So we'll set up this problem with a single source. To do that, we're going to import this time axis, and this is essentially because we need to know the source injection intensity at each point in time. This is essentially just a linear. This is just a function which contains the strength of the source at each of the time levels of our simulation. Model dot, and then so we specify the initial time. So we'll start our simulation at t equals 0, run it forward to t equals 1,000 milliseconds. So it's going to be a 1 second simulation. And this model dot critical dt is just called, well, this just works out the stability condition for the acoustic wave equation in the particular domain. So just calculate your according to the highest velocities as it sees in the model. That this is just the standard stability criterion for the and it works out based out on the standard stability criterion for the acoustic wave equation. But you can of course set dt to be as you wish. We're just using this. We're calling this function here, but we could manually set this to choose it as we like. And of course, just a reminder that if we want to look at the actual documentation for the time range to see what it offers on top of being this 1D array, which is contains a point for each time level within our simulation. There's some additional information there. So now we'll import our Ricker source object, and what this is going to do then, we're going to pass it our time range, and it's just going to work out the value of that mathematical function for the Ricker source we wrote down above, and just fill in the NumPy array with these different time levels with the appropriate values according to our equation. So we define the peak frequency of our wave. Here we're going to choose that to be 10 hertz. Then we say SRC equals Ricker source. We give her a name, tell it which grid it exists on, tell it the peak frequency, tell it how many points we've got. So here we just want one source. And so we'll just create, so this then is telling it it's just got one source position. And then we'll give it the time range, and this is again the discrete points in time at which this source knows its values to inject into the simulation. Now then we need to set the coordinates of the source. We can set those by accessing the coordinates property. If we say src.coordinates, and then we set the data of those coordinates. The first index here is the source number. We only have a single source, and so that corresponds to index 0. And then the second is the coordinate in each of the dimensions. So 0 here corresponds to the x coordinate. So we're setting this to be right in the center of the domain in the x dimension. and then 1 corresponds to the y coordinate, or the z coordinate, the depth coordinate, if you want to think of it that way. And so we're setting this to be, this our source to be right in the middle in the x dimension and at a depth of 20 meters. This is the signature of the source. This is a Rickel wavelet with a peak frequency of 10 hertz. And before we sort of view where our sources and receivers are located in the geometry, let's just, let's create our receivers. So we have a similar object to the source object. So we say REC equals, we call the receiver object. Then we give it a name, tell it which grid it's on. And now we're going to have 101 receivers. And time range here is going to tell it at which points to record the wave field throughout the simulation. So time range here is just telling it record the wave field at each point in time. So one of the differences then between sources and receivers, as we'll see, so sources have this inject property. And there is, they're going to, this has, they have a property, so we, sources and receivers don't have to necessarily be located on computational grid points. They can be off grid. And so a source, when we're injecting it, it's going to linearly interpret the source value onto the surrounding grid points. And for a receiver, we're just linearly interpolating the wave field from its surrounding points onto that receiver location. And so if we plot our domain, this is the setup we're dealing with. So we've got a source indicated by the red dot here right at the center of the domain. And then we've got these 101 receivers equally spaced along the top of the domain. Here we're just plotting 1 in every 4 receivers, so there's just 25 receivers plotted in this particular image here. So now let's look at the finite difference discretization we need for our problem. So for the time discretization, we'll use a second order discretization in time, given by the expression here, which we can get Devito to compute via the u.dt2 function. The spatial discretization is just sort of a general expression of the finite difference equation. But here we'll just be using u.Laplace then to compute the Laplacian of our wave field in space. When we work out the time stepping scheme, so if we put our discretizations into the wave equation explicitly for the time derivatives and the spatial derivatives, we rearrange everything so we've got our field at t plus dt on the left-hand side, everything else on the right-hand side. We end up with the following expression where we've yet to sort of write down the explicit time discretization. But the important thing to point out in this scheme is that this Q here is our source term, and because of the nature of the scheme, we need to multiply that by delta t squared divided by m. Remember where m is 1 over c squared, right? So when we inject into our domain, we're going to want to inject our source into the forward wave field. So the value of the source is going to need to be multiplied by this delta t squared over m. And it's coming purely from the rearrangement of our finite difference scheme into this forward time stepping scheme. So let's set up this time stepping scheme now. So we'll import the time function from Devito. We'll set u to be equal to this time function, and we'll give it a grid and tell it the time order and space order. Now we can write down our PDE, which is model.m times u.dt2, is the second derivative of u with respect to time, minus the Laplacian of u, and then we're going to add on the damping term. So we can grab model.damped from, so when we've created our model, this is sort of created this field, this eta, which again has a value of 0 in the main computational domain, but then is ramping up within the boundary layers, these final 10 nodes on each extent. of the spatial dimensions. And if we write down our PDE, you see we get the following, which is just what was just the wave equation we wrote down above. We can form our time-stepping scheme in a similar way. We can create an equation. We can say u dot forward is equal to solve PDE for u dot forward. And then that is going to create this, the time-stepping scheme we wrote down above. And now we need to create our source injection term and our receiver term. So for that, we can say SRC term equals source.inject. Then when we choose this, again, this is not put within the main PDE because this is an off-grid operation. It's a sparse operation, which is not necessarily associated with any particular grid point, so we need to deal with it in a slightly separate way. And we can say src.inject. We tell it what field we want to inject the source into. So we want to inject it u at t plus dt, and then the expression for the injection. Right? And the expression is our source term, SRC, and then times this delta t squared divided by model dot m. Of course, when you work out your discretization on pen and paper for any particular problem, any type of wave equation, just looking at that will tell you the expression you need to put in here. And then our receiver term, we just want to here interpolate the wave field onto our receiver points throughout time. So we're just going to, the expression we want for our receivers is just u dot forward. But of course, this expression could be sort of arbitrarily complex as well. So now we can construct our operator, and so just a note, sort of here in the below, we're going to use the argument subs equals model dot spacing map, and this causes the operator to substitute values for our current grid spacing into the expressions before code generation, and so this reduces the number of floating point operations executed by the kernel by pre-evaluating certain coefficients. So that's just to say that if you have something as a symbol, you can always substitute in, and that symbol is going to take a particular value throughout your simulation. You can always substitute in a value for that symbol prior to code generation, just to remove those symbols from the code and reduce floating point operations a little. So we say operator, pass it our list of equations. Again, remember that this plus has nothing to do with any mathematical plus operation. It's simply sort of adding lists together in Python notation. And this is telling it just to remove this dx or the hx and hy terms and replace them with these particular numbers, which are the grid spacing in each of our x and y dimensions. So now we can create and execute the operator for a number of time steps. And so here we're going to tell it to execute the operator from remember this is just a shorthand for time underscore big M, and we want to run for time range. We want to run for the number of time steps. We want to compute the wave field for the number of steps for which we define time range, and so the final iteration we need to do is to compute at time range number -1, which will then compute everything for the time step of time range number. And then we're going to pass it dt as to be the critical time step. and then we can execute that code. And then if we want to plot, or if we want to look at the shot records for created at our receivers, we can import this sort of plot shot record helper function, run that, and then here we go. This is the plot we're getting. So here we're seeing the sort of the initial wave in the central receivers, and sort of we get this linear arc propagating out. And then we start to see the receivers picking up reflections and so on at later times. And I did have let me just find another plot of the wave field. And so there we run the simulation for all time and looked at the shot record, and that was 1,000 time steps. But here, and this is just this plot here is just showing this is after 100 time steps, just showing the wave field sort of propagating out. Okay, so let's, I guess, take an 8-minute break. Now, and then when we come back, we'll go on to the final notebook where we build the FWI algorithm, sort of incorporating this forward wave propagator with a few additional things. And just as a note here, just with regards to sort of running DeVito simulations with MPI. So one of the design ideas of DeVito is if we want to run on a different architecture, we want to run with MPI or whatever, there are 0 changes you need to make to the user code. So the code we've written, or the code which you'd run on your laptop on one processor, then that you could translate that main code to sort of any architecture, run it with MPI and so on. All we need to do is change a few environmental variables, and DeVito will do the rest for us. So if, for example, we wanted to run a wave propagator with MPI, we just need to add the environment variable DeVito MPI equals 1 MPI argument, and then execute your script. So there's an acoustic in the additional material folder. If you're interested in playing around with this, there's an acoustic script.py. You can see that you can just run Python acoustic script.py, and that will run it on in serial on a single processor. But if we want to then run that with MPI, we can just do this quick modification to our command we run, and we'll run that script, same script, but with MPI now. Okay, so let's get back to defining our computational domain. So we're going to create a grid where the main section of our computational domain is 101 by 101 grid points. We'll have a spacing again of 10 in each of the grid dimensions, and we'll set our origin to be equal to 0, 0. Here, we're going to create 2 models. So this one we'll call model is our true model. So this is going to have the true velocity model associated with it. And we're going to use, for that, in this case, we're going to use a simple velocity model where we have a region, a circular region in the center of our domain, which has a velocity of 3 kilometers per second, the velocity of pressure waves, and the surrounding area will have a velocity of 2.5 kilometers per second. Then we're going to have our initial guess model, which we'll call model 0, and this is just going to have a velocity of 2.5 meters per second throughout the domain to start. So, of course, you can see, hopefully, as we move through our FWI iterations, we're hopefully going to move from having this completely flat velocity model to starting to resolve a circular region in the center of the domain. For this, we're going to use 40 grid points in each of the boundary layers. And so our computational grid in this case is actually going to be 181 by 181 nodes. So we're adding 40 on each extreme of the computational domain. So let's set up our acquisition geometry now for the problem. For this, we'll just do a simple transmission problem. It means we'll have our source on one side of we'll have our sources on one side of the domain and our receivers on the opposite side of the domain. So we'll start our simulation at t equals 0 again. We'll finish at t equals 1,000 milliseconds. Again, we'll be running for about 1 second. And we're going to use Ricker wavelets as our sources again with peak frequencies of 10 hertz. So that if we want to, let's define our source coordinates. So initially, we'll do this test run with a source right in the middle of the domain, but then for our shots, during our FWI loop, we'll move this source along the left boundary. I'll have a picture of that down below. But just to sort of show an example with a single source to start off. So again, we're setting our source coordinates here. So we want we're just going to have a single source at a time. So to access the first source is indexed. We get the 0 here. Then we're setting to have be right in the middle. Well, here it's going to be in the y dimension, and its x dimension coordinate is going to be at 20 meters. And we're going to set then the receivers to be up on the right-hand side of the domain. So here we're just setting the source and receiver positions and the numbers. Again, here's the signal for Ricker wavelet, and this is then the setup we've got. So during our FWI simulation, we're going to be moving this source along the y dimension with a fixed x position, and then our receivers are going to be located along the right-hand side. So let's run a quick forward simulation with our true model and our initial smooth model, and let's look at the shot records in each case. So here, now we're using this solver, or we're using this acoustic wave solver class, and this is again, this is just a class built using the DeVito DSL to have all the operators we need for a FWI simulation. It knows about, well, it has methods associated to do the forward solve, the backward solve, and then the gradient computation. And so if we call this solver and to solve the forward problem for us, and we pass that then the true model, and we'll also call the solver and we'll pass it our initial smooth model, and then we'll plot the shot records in each case, and then also the data residual. So this is a picture of the shot record with our true model, i.e. this is like the recorded data, the field data in a real scenario, and then this here is the shot record with our initial smooth model, and then this is then the data residual, the difference between our true and smooth models. So just a quick review of then what the FWI algorithm is going to be doing. So we want to think about the adjoint wave equation. So we could think of this, well, when we think about the discretization of our acoustic wave equation, we could write that as, you know, some matrix A, which is dependent on only the model M, multiplied by or operating on our wave field U, where this U here is one big long vector containing the wave field at all points in space, at all points in time, is equal to then the source term on the right-hand side. And then we have the backward propagation equivalent using our residual wave field. So we can set up our forward propagator such that its transpose, this gives the backward propagation problem, and then sort of operating on the residual wave field labeled V, or to compute in the residual wave field labeled V here, where we're using then now the residual as virtual sources, and so that contributes the residual is contributing our right hand side too. And then so what we want to do during the algorithm is minimize our objective function phi, which we said is the L2 norm of the data residual, or we could look at that, of course, as sort of this this what we call the restriction matrix, and operating on the full wave field U. So the restriction matrix is just the operation which pulls that data of the full wave field onto our receiver locations, minus then the recorded data, the L2 norm of that. And then when you go through a bit of linear algebra, it tells you then that you can compute your wave field via this term, via this equation here. And the gradient operation which we need to compute, then sort of this is what is going to contain our residual wave field U, and this VTT term is just the derivative of the finite difference propagator, and this is just something we can compute analytically, or it's often people write that as the JT delta D in that form there. Okay, but is there anything else to point out here? But yeah, basically what we're going to need to do to in the algorithm is compute the forward wave field U, then use that to compute the data, compute the data at the receivers, and then in order to compute the gradient, we'll need to compute the backward propagation using this residual data, plug it into some operations, and then I'll spit out the gradient for us. But here, as I mentioned, conveniently we've got this DeVito gradient function, which we'll just use, which we feed it the appropriate objects, and that's going to compute this thing for us. So in order to compute the gradient, we'll need to simulate the forward wave field with the background velocity model to get the synthetic data and save the full wave field U. So the gradient The gradient computation relies on knowing your full wave field U. Compute the residual data, backpropagate the data residual, and compute the on-the-fly gradient contribution at each time step. So this procedure is applied to multiple source positions, and then we sum these things up to get the gradient of the image, of the subsurface image. We again prepare the source location for each shot and visualize them. Also, so that here we're gonna look at what the gradient computation looks like for a single shot before actually going through our full FWI iteration loop. So in the actual FWI iteration loop, these are the shot positions we're going to use. So we're going to move I think it was nine shot locations. We're just going to move our source along the y-axis 20 meters in from the X boundary. And then here are some functions we're going to need to make use of during our FWI loop. So this function here is just to compute the residual. This stuff here is just so this function works with MPI. So I guess the pertinent line to look at here is just that our residual data is the synthetic data minus the observed data. This is just a function to give us our delta D. And then we've got the FWI gradient function. And here we're going to define a function called grad. This is going to need the data residual. We'll define a set of or a receiver function to be able to record that. And then we're going to define our observed data and our synthetic data. So our objective function is going to be initially 0. So there this is just resetting our objective function before we compute all the contributions to it. And then here's our loop over the shots. So we're going to say for I in range n shots, this is where we set the source position for that particular shot. So we're just sort of iterating along those source positions we drew above. First, we compute the forward wave field, which we're going to store in this variable u0. So we call solver.forward. Also, this is computing the true data. So this is our dobs. So we call solver.forward and just record the true data. Then we call solver.forward again, but using our smooth model, recording dsyn, synthetic data, but we also want to record the full wave field here, which we're going to store in the variable u0. With those things computed, so that's all the components we need to then sort of before we call our gradient operator. So we're going to compute the residual. We're going to, with the residual, we can then compute the L2 norm of that and add it to our objective function for this particular FWI iteration. And then we can call this solver.gradient. And for that, we need to pass it the residual data, which is it's going to use to do the backpropagation. And also for the mathematical operations it needs to do, it needs the full wave field. So we're going to pass it that, and then we also need to give it the model, which is going to use for those operations, and then we're just passing it the function on which we want it to sort of return the gradient contribution from that shot to. So we're just telling it. Remember, we defined this grad above, and it's saying sort of put your gradient computation into this particular function. And then this is going to return sort of the objective function and the grad. So this data, this compute residual and FWI gradient are going to be sort of two functions we need to repeatedly call during our FWI loop, which we'll define below. define the full loop, let's just look at a single gradient computation. So if we set our source, I think, to be in the middle of the domain, and we call this we call the FWI gradient function. Then we can plot the minus update.data. So this update is the gradient, and we can see for the first shot this is the gradient which is being computed for this particular model. So you can see that it's starting to sort of it's demonstrating this circular region in the middle. And again, this is our just what was that bit? Then this is the difference between the two models. Again, and this is what things would look like after a single update. Then we need to define our. Do I have any more details about that? No. Then we need to define our sort of gradient descent update scheme. So for that, we're going to define this function called update with box. So dm here is minus the gradient. And so our gradient descent scheme, we're going to be we're going to add some alpha times the minus the gradient to get our updated model. And then we're going to call this equation, which applies this update to our model. But we're going to have some, in any real scenario, based on your sort of knowledge of the geological region, or if you're doing some medical imaging problem, you know roughly what the maximum, minimum speeds of any particular velocity waves are in the tissues involved, or the rocks involved, and so on. Based on the sort of knowledge of the geology of the area. And hence we can sort of apply this box update where we say, well, if we get any, after an update, if we get any areas, then we're going to just reset them to be within these sensible bounds. And so we're going to apply the standard gradient descent update scheme, and then just ensure that no velocities are less than our minimum defined velocity, or that none exceed some maximum defined velocity. Okay, so now we're ready to actually form our FWI loop. So we're going to import this function called mmax, which just computes the maximum, or like the absolute maximum value of some function. So it's just like if you had a pure numpy array, it's just doing like abs of that array and then max of that. But of course, numpy doesn't work in parallel, so there's like this is DeVito equivalent, which would work in parallel. So now, and we're going to record the objective function at each FWI iteration in this array we've defined to be history. So now we're going to do our FWI loop. So we'll loop through from 0 to the number of FWI iterations. So first thing we need to do then in the loop is compute our gradient and objective function. So the objective function we've labeled phi, and this direction is minus gradient. Then we'll record what our objective function is for this particular iteration in the array we've created history, and then we need to do our update. Here again we'll use an artificial step length. So we'll just use here an alpha of 0.05 divided by mmax or mmax direction. So we're just going to be scaling by the largest value or the largest absolute value appearing in our gradient. And then And then we'll call the update with box, where our gradient descent up scheme is applied. So we'll update our smooth model, and we'll pass it our choice of alpha, and we're going to pass it direction, which again is minus gradient. And then we'll loop through that, and we can see the initial objective function. Again, this is the L2 norm of our residual data. Initially, 39,291 point something. Then after 5 iterations, that's reduced to 3,960. And if we print our final model, we can see this is where our model is finishing on. So we're starting to resolve that central region, and it's carrying the velocity in that central region fairly correct, up towards the 3 kilometers per second range. And then here's just looking at the history of our phi value, where we see that our objective function is then decreasing over time. And of course, there are various things we could do to improve this result. But this is just sort of a starting point, and then you can go around and play around with stuff and see how you can improve this particular result here. Okay, and that sort of covers all the material for today's session. So just to say before we finish up, thanks again for everyone for attending. If there's any questions you have, feel free to ask myself, Ed, or Zoe. I would be very happy to sort of help out with anything. And just to sort of point you towards, if you're interested, point you towards the Devito website. So we have our project page here, devitoproject.org. If you're interested in finding out more about the Devito project, this has got links to our GitHub and various other things, and also a link to join our Slack channel. So we have a very active Slack community. If you have any follow-up questions at a later point, at a later date, please feel free to sort of join our Slack channel. There's an active community there. We're always happy to answer questions, and we're also always happy to get new members and users joining that channel. Okay, so yeah, thanks very much, everyone.